My name's Daira. I've invented a programming language called Noether. But what I'd like to talk to you today is to try and convince you of the importance of symmetry in programming language design. So I'm not just describing Noether, I'm using Noether as an example of this approach to designing languages and how it helps. And I'm going to be talking about that in general, and then going through the sublanguages of Noether in order of decreasing symmetry. And maybe, if we have time, some discussion of how to implement things efficiently. Can everyone hear me, by the way? Okay. Okay. Is that better now? Yes. Thank you. Okay, so what do I see the problem as being in facing programming language designers? Well, computers have become huge in terms of their power, the storage capacity. We need languages that can express powerful abstractions in order to reduce complexity. This quote by Dijkstra, which is too long to read, is wonderful. So he's saying that in 1972, because the size of computers had increased by 1,000-fold, that they were too complicated. Well, since then they've increased by another 1,000,000-fold. And in terms of storage for a given price, that's improved by, I think it's 7 orders of magnitude. So, have languages and tools improved enough over that time? I don't think so. I think we're still in a software crisis because our programs are too large and complex. We don't know how to write correct, secure, and reliable programs. Importantly, we don't know how to write them at economical effort. So, to get back to the political point about the NSA has been successful in exploiting security flaws in widely used software because the tools and languages that we have are not good enough to be able to write secure software. In practice, I mean, you can, if you spend enough effort, if you do the kind of things that, say, NASA is doing software that uses on the space station, then you can write secure and reliable software. No one does that in practice, apart from NASA, a few others. So I claim that correctness, security, and reliability are 3 sides of the same coin. It's metaphorical coins that can have 3 sides. And we have techniques that help with this, like pure functional programming and object-oriented programming, but we need to understand how they help. And I think the way that they help is by imposing symmetries. So a symmetry in general, the kind of symmetry that you might have learnt in junior high school or whatever, are geometrical symmetries. So if you change a shape in a particular way, then you get a similar shape. Similarly, you can change a program in a particular way and get a similar program. So in the simplest case, a program that does the same thing. This concept also applies in physics. So there's charge parity time symmetry. You change everything to antimatter, swap things, mirror things in space, and change the direction of time, and everything works out the same. Okay, in programming, you have lots of very interesting symmetries that apply, or that nearly apply to practical programming languages. Some of these don't actually apply to full programming languages that people use in practice because they have these particular warts and special cases. And what I'm trying to claim is that we should pay attention to those warts and special cases and try to reduce or eliminate them. So some examples, you've got confluence, which is that in a pure functional language, you can evaluate things in different orders and you'll get the same result. And you can move pure functions to different parts of a program and they'll still give the same result. So, and you can have symmetries that are associated with particular operators and functions. You can rename variables. You can add and remove annotations. This is an interesting category of symmetries. For example, functional abstraction. So you can take inline code, extract it to a function, and call that function, and that will give you an equivalent program. And similarly with macros and modules and type synonyms. Okay, an obvious one at the end, which is almost too obvious to see, is comments. You can make arbitrary changes to the comments in a program and it won't do anything to what the program does. That, by the way, is not true in C. Because of the textual macro system. Okay, so many languages and properties interfere with symmetries that we would like to have in our language. And some of those interfering features are really quite important. Things like side effects, state, failure handling, and concurrency. And some of these other ones, well, we can leave those out from a language perfectly fine. No one uses dynamic binding anymore. Implicit coercions. If you've ever used a language with implicit coercions like JavaScript, I mean, I know JavaScript is our favorite language to bash. The implicit coercions cause a fair proportion of the bugs that you end up introducing. And features that are unhygienic in the sense that they break abstractions. So for example, if you have a function in some languages that will be opaque, but in other languages you'll be able to extract its code, change its code, do reflection on it, and that breaks symmetry. And of course, anything that violates memory safety. Okay, and you can end up misdesigning a feature so that it doesn't have the symmetries that you would naively assume that it would do. So one of the things we can do is just leave out these features. And that gives us a simpler language. So if we possibly can leave out these features, then we should. But what about the ones that we really need, like side effects, failure handling, and concurrency? I'm going to claim that we do need concurrency. I know some languages do without it, but it's becoming more and more important. So what we can do about this is to define stratified languages. So languages with different levels of complexity. So an inner language that's, say, a pure functional, and all functions terminate. And at the outer level, you have mutable state, concurrency, failure handling, everything that you would expect in a full language. And my claim is that usually for practical programs, you can write most of your code in the inner languages and use the outer ones as a coordination language. And the claim is that this will give you a program that is overall easier to reason about. And obviously this is not a new idea because it's the idea behind Haskell. It's to some extent the idea behind Erlang, which has a functional language to define processes and then a concurrent coordination language. So that's the idea that we're using, but we're going to take it further. And at each level of the language, we're going to add features and we're going to break one of the symmetries that we had at the previous level. Some of these symmetries, they're so useful that we shouldn't break them at all. For example, the actor locality laws are a set of laws that define or constrain how information propagates through a program, or how authority propagates through a program. This was work done by Carl Hewitt and Gulager in the 70s, I think. And they're really very important for being able to constrain what programs in a language can do. So we want to retain those in the full language. And there's a trade-off between keeping the number of levels small to keep it understandable and sort of optimizing the curve, which gives you a given expressiveness for a given symmetry. But we can always collapse the levels later. I'm going to be short on time, so I'll skip some of this. I really encourage people to read through the slides in detail because they're very dense, as you may have noticed. And they'll be on the web, obviously. So, I've lost my track. Yeah, there's another issue which happens when you have a stratified language. Are you retaining the properties of the inner languages when you compose them in the coordination language? It's important that you do, because otherwise you lose the advantages of stratification. So an analogy of this, if you consider the inner languages to be an ordered state of matter like a solid, and the outer languages to be a gas or whatever, then if you move a solid within a gas, it retains its shape, its rigidity. And similarly, what you want to happen is that when you move subprograms that are highly ordered within the coordination language, that they also retain their properties. And it's easy to end up breaking that, actually. Yeah, I'm going to skip this slide. Okay, so the Noether language, it's an object capability language. I don't know how many of you are familiar with that, but it's an approach to security which basically says that if you have a reference to something, then you have the authority to operate on that thing. So it avoids having a separate layer of access control because the flow of authority within the program reflects its functionality. You don't need to add extra access control on afterward. It's parallel, it's concurrent. I've separated those two because concurrency is really complicated. It's really complicated to reason about. But parallelism for efficiency can be done in a pure functional language. So if we separate those two, then we're optimizing the symmetry expressiveness. Okay, and I'm only going to talk about semantics. I don't really care that much about syntax. And we can use the syntax of any language we like. Okay, those are the reasons why I think a new language is needed. Okay, why is it called Noether? Well, Emmy Noether was a physicist did most of her work in the 1920s and 1930s. And she was well known for her study of symmetry in physics and in mathematics. And actually, there are some technical reasons why her work applies directly to Noether, because we can consider the inner languages as a Noetherian rewriting system. And we can also use analogies with physics like we have done. So I'm going into a lot of detail on this slide, and there's quite a bit of mathematics on it. I encourage people to look at the mathematics later, but it's not practical for me to explain all of it here. Basically, what we're doing is modeling the execution of the language as a rewriting system. So we rewrite terms to simpler terms in order to model evaluation. And we need to go into this much detail and take this much care about it in order to make sure that we get the symmetry properties that we want. Very easy thing to make mistakes with. I'll just point out a bit of the notation that I'm going to be using later. This 3-line Swiggle equivalence operator is one of the most important things, because what that says is that two programs are equivalent. And they're equivalent in any context that you might use them. So Noether is a non-deterministic language in general. And the way it handles failure is that any program is allowed to fail. If it's deterministic, then it gives a single answer or it fails. And I think that's necessary because we need to be able to model cases where real computers fail to satisfy the ideal model of a computer. For example, they've run out of memory, or the network breaks, or there's a hardware failure, or whatever. And if we include that within our model of the language, then we're being more realistic. Okay, so symmetry properties that always hold, basically alpha renaming. Properties that might hold in particular subsets. So a lot of this is basic computer science, really, but we need to be careful about the case of failures, because a lot of the work that's been done in fundamental computer science doesn't really consider failures very well. It considers terminating languages that always give you a given result, which isn't actually very realistic. Okay, so these are properties that might hold for a pure language. This one is interesting, unfoldability. Basically, it says that if you have a function definition, and this Vx means some expression that uses x, and you have s and t, which are equivalent expressions, and you substitute s, you call f with expression s, then you get the same thing as expanding the function body with the equivalent thing t. So that's called unfoldability. And it's basically the essence of pure functional programming. Sometimes people say that referential transparency is the essence of functional programming, but these two things do not actually imply each other in a non-deterministic language. Okay. Right, so this is the structure of the overall language. So we have the most structured subset on the top left there, which is Noether P. And that already includes parallelism, because it turns out that parallelism doesn't break any symmetry properties. A parallel program can do exactly the same things as a serial program and be just as easy to reason about, because the parallelism is in some sense automatic. And then we add features in turn. So we add failure handling, and as we add failure handling, for example, that breaks the execution order independence. Because obviously, when a failure happens, affects which failure you get. These two languages, the red and orange ones, are not even Turing complete, because you can you can do a lot in languages that aren't Turing complete. So most programs, or most subprograms, are intended to terminate. And even when you have a large program, say for example, a web server, each request to the web server is intended to terminate. And almost all of your code is in the handling of those requests. The bit that sort of loops over requests is in a framework, probably. And then we add some less interesting features. Then we add mutable state. So when we add mutable state, we no longer have a functional language. And so we lose all these symmetries that are associated with functional languages. And after that, we add concurrency. We first of all add concurrency in a form that's very easy to reason about because it's basically static data flow. So one of the talks before was saying that we want fixed data flow networks in order to be able to reason about them. Yes, that's true, but it doesn't mean that the whole language has to be restricted to fixed data flow. And then on the outside, we have an event loop language. So I don't know how many of you know about event loop concurrency, but it's basically the language that's used or going to be used in the model that's going to be used in JavaScript in lots of web applications. It's used in languages like E and sort of Erlang. So it's a very expressive model, but it's not the same as shared state concurrency with threads and locks, because those turn out to be impossible to reason about. I mean, I know some people have tried with type systems that try to ensure locking. I don't think it works very well. Okay. Influences on Noether, all those things, but we haven't got time to go through them. Okay. A lot of the languages that are sort of have a reputation for being safe languages, things like Haskell, OCaml, they have loopholes. So here are two examples. In OCaml, there's this module that's part of the standard library, which is to do marshalling and unmarshalling, also called serialization. And it's unsafe, and you can very easily crash the whole program by using it. Similarly, in Haskell, you have unsafe things like unsafe perform IO. It's really good that they have unsafe in the names. I mean, it's not trying to mislead anyone, and you have to import them from the unsafe module, so that's fine. But they still do crash your program if you use them. A subtle point here is that these primitives are used all over the Haskell libraries. So even if you have a pure functional program, if you use things like statements or whatever, they're going to be using this under the hood, and you have to rely on the fact that the library writers have used them correctly. And if you look on the Haskell wiki, there's a bunch of conditions for how to safely use unsafe perform IO, and they're very compiler dependent and implementation dependent. So the basic problem here is that we have a lack of expressiveness in how to do these things safely. So for example, the actual thing that this program is trying to do needn't be unsafe. And similarly for the OCaml example, there are ways to do type-safe serialization and unserialization, but this particular OCaml library didn't use them. Okay, so by designing a language in terms of symmetries, they keep us honest in language design. So for example, suppose we want to avoid implicit coercions. There are some behaviors that we might include in our language that are like implicit coercions, but because they're not like what we recognize as an implicit coercion from other languages, we don't know that that's what we've effectively added. But that kind of thing will end up breaking symmetries. And we'll have to either explicitly include that feature in another level of the language, or we'll have to avoid it entirely. So, as I say, it keeps us honest in the language design. Okay. So even in safe languages, there are certain kinds of language properties that make it much more difficult to avoid bugs. So, for example, if you have a language with modular arithmetic or floating point arithmetic in place of integers, you're going to have a mental model in your head of what addition means that is basically mathematical addition. And if you implement that using an operator that actually does modulo addition or floating point addition, then you're going to make mistakes. And this is an example of an actual mistake that's made in secure ECMAScript. Basically, there was a corner case at the top range of the set of integers that can be expressed as floating point exactly. And the problem here is divergence from intuition. I'll just say how Noether addresses that. So don't have operations that do the wrong thing. And this is actually quite hard. But remember that operations are allowed to fail. So instead of doing modular arithmetic, for example, we can have an addition that fails if you get the wrong answer. Supporting programming without state, because state is one of the things that if you get into an inconsistent state, then it's very difficult to recover. If you didn't use state in the first place, then you have no inconsistency. And transactionality. So transactions are probably familiar from database programming. And to some extent, they've started to be adopted into language design, things like software transactional memory. But they haven't made much of an inroad into commonly used languages. They're still sort of a research project. And a big reason for that is performance. So most software transactional memory systems, for example, have, if you try to run them on two processors, then they're, I don't know, 10, 20 times slower than running on one processor. So, but we can do transactional programming efficiently, and if I have time, I'll explain how that's done. So, I mean, a lot of the compromises made in language design are because of performance or perceived performance. So, if you remember the slide from near the beginning, where the performance of computers had increased by 1 million-fold in 30 years, you might think that no one should really care about performance anymore. But, as Daira said, we're trying to solve more difficult problems. In your smartphone, for example, you've got all of this graphics and bells and whistles that it's trying to do at the same time as computing something, and the actual computing something may be quite trivial. But because of all these bells and whistles, it's still not necessarily fast as you perceive it to run. Yeah, another quote that I love about security. So Hoare gets it spot on here. He says that every syntactically correct program should give a result or error message predictable and comprehensible in terms of the source language. So if you need to understand the implementation in order to understand the errors that your program is giving you, then you don't have very much chance of fixing the bug. And it's possible to design that problem out of languages, but there are still far too many languages in common use where that's not done. I mean, C is very, very commonly used still. But it's not just C, it's lots of failure cases in even languages that are perceived to be more safe. Okay, so let's go into detail about the actual languages that are part of Noether. So we start off with a deterministic, strict, pure functional language where everything terminates. Remember that failure is always an option. So we either succeed and give a single answer, or we fail in a finite time. Failing in a finite time doesn't mean that it's going to fail in a practical length of time. But my claim here is that if we write in languages that are terminating, then we'll understand better what the even though we're not guaranteed to terminate in a practical length of time, we're less likely to make bugs that cause us to have infinite loops, because we can't do that in the language. So we will understand the performance better, even though the language isn't controlling performance per se. And actually, we can add later security features that allow us to control performance as well, but that's a separate problem. Okay. As more justification of allowing programs to fail. Symmetries are associated with equational reasoning. So, okay, the program is deterministic if its outcome and side effects are dependent only on its input state. Determinism is a weaker property than being pure functional. You can have a deterministic program that still uses mutable state, that still has side effects, but they're always the same side effects every time you run it. So Noether 0 is deterministic, but so are quite a few of the larger languages are also deterministic. Okay, we've gone through time location invariance before, so you move a pure program to a different place, then it computes the same result. And that also applies if you move it to a different task in the concurrent languages. If you remember before, we were talking about coherence, the property that sort of structured subsets retain their properties. That's an example of that. How are we doing for time, by the way?
About 5 minutes-ish.
5 minutes more?
Yeah.
Okay, right. So, okay, so because we don't have mutable state and because all programs terminate, we can treat definitions within the program as equations. So, for example, here we have a program that doesn't terminate, and so would be excluded from this subset. And because it doesn't terminate, this attempt to use equational reasoning fails, because we subtract loop x from both sides, we get 0 equals 1. And that fails because the program didn't terminate. So the property that Noether 0 actually has is definiteness. So that's the fact that a program gives a specific result or it fails. you might say, if we're not enforcing success, then what's the advantage of that? Well, the advantage is that we still have this unfoldability reasoning property that holds even if in the case of failure. That's actually the same unfoldability property that we discussed before. I haven't updated the slide to say that. And if a program fails, we can recover from that. If it goes into an infinite loop, then detecting that is possible, but the problem is that you have to use something like a timeout. And a timeout makes your program non-deterministic. So you lose the symmetry property either way. So how do we prove termination? Well, we do it automatically. Termination proving is a well-understood problem. I think a lot of people have the impression that non-Turing complete languages are useless. Actually, you can say so much without Turing completeness that it's likely to be only a tiny part of your program that can't be automatically proven terminating. I've already gone through this about bugs that cause excessive runtime. So the next thing we add to this sort of strict sequential pure functional language is parallelism. This is an approach that has been researched originally in the Silk language. It's now an Intel project called Silk Plus, called fork-join parallelism. And the property of this is it allows you to run things in parallel, but it has exactly the same semantics as a serial program. Actually, the original Silk, that statement wasn't quite true because a program could have race conditions, and in the case where it has race conditions, then it doesn't behave the same way as a sequential language. But because we're enforcing these extra symmetry properties, we can guarantee that there are no race conditions. And like I say, that not only does this give parallelism, it's actually quite efficient in practice. And there's been lots of research on how to do this well using work-stealing schedulers. And they produce, well, not optimal results, but sort of within a constant factor of optimal scheduling. Okay, and yeah, like I say, improvements over Silk, we have identical parallel and serial semantics. And the restrictions we make relative to Silk aren't going to be a problem because we'll add full concurrency later. Okay, yeah, we're running out of time. Okay, this is a justification for why we want explicit parallelism annotations rather than having everything be inferred. The next thing we add is local mutable state. So that's mutable state that only applies within a function. And because it only applies within a function, we could compile it out. We could produce an equivalent pure functional program. So although it makes that particular function more difficult to understand, it's not making the whole program more difficult to understand. Although it does break some symmetries. There's this interesting symmetry called tenant-landing correspondence, which is basically sort of inlining functions. And this doesn't quite hold because of the mutable state. So we have lost something. The next thing we add is failure handling. So failure handling in Noether is transactional. If, like in a database transaction, if you get an integrity violation, then the transaction you're in will be rolled back. Now, in Noether, that applies to every function call. I'll explain later why that isn't as expensive as it sounds. So this is not like exception handling. With exception handling, if you get an exception, then the state may have been updated by the point you get the exception. Because you lose information about exactly when the exception happened, it's actually very difficult to recover from that inconsistent state. In Noether, it happens automatically. So C++ programmers call this the strong exception guarantee, and in Noether, you have it automatically for every function. Okay, and we lose another symmetry about evaluation order there. Yeah, we're not going to have time for this.
Sorry, we need to wrap up.
Okay. So you then add true incompleteness next, and then you add laziness, and then static names, which are they're like nonces in Oz, if you know what that is. And then you add reducers, which are a way of, they're a weaker form of state. So they're more easier to reason about than full mutable state. Okay, and then we add full state. We only add task local state. So as in languages like Lang, which is message passing concurrency, we have no state that is shared between different tasks and can be accessed directly. Transactions. Okay. I'm not going to have time, obviously, to justify why transactions are not too expensive. So you have to read the slides afterwards. There's a detailed justification of that. The next thing we add is data flow concurrency, but we add deterministic concurrency. So basically, the restriction here is that because you're only waiting for one possible event, everything is deterministic. Okay. And then eventually we add the whole thing, message passing concurrency and event loops. Now, the language that we have at the end here is still quite easy to reason about. It's similar to languages like E and Joule and Erlang. So it's still completely memory safe. It doesn't have race conditions, or doesn't have low-level race conditions. It's pretty easy. Well, it's never easy to write secure programs, but you're more likely to be able to write it than in some other languages. Okay. And there's a distributed extension which has the same semantics as the language on a single machine, and this uses a protocol called CAN, which is almost magical in its ability to recover from failure. But you can read about that later. Okay, and lots of security features, confinement, whatever. Okay, questions?
Let's take questions at lunch.